So once again, it is pretty amazing to think that in a transverse wave, all of the motion is just up and down, even though the waves are traveling left to right. And I guess in a field of wheat, you can imagine the wheat shaking around and a whole pattern going across, but obviously the wheat doesn't get up and move along. And in the same sense, when I speak, the air doesn't actually come from my mouth and go all the way up to the back of the room and go into your eardrums. It's just the air particles vibrate, and that vibration is somehow moving. The energy moves, but not the particles. And this was just showing that I am keeping track of everyone's learning catalytic scores, and this was the leaderboard. So everyone, these are people that I just thank you for showing up every day. It's really awesome. Not only showing up, but also answering my questions right, and there was a free hoodie that went off to Ingrid, so well done on there. Anyway, so moving on. You don't know that I'm keeping track, but I do. I keep track. I care. And I think it is a lot of work to battle the snow and to come here every night and listen to me go on and on. So I appreciate it. It has been fun. So let's do a little series of quick little learning catalytics, and I'll put these up on here. So wavelength is the distance over which a wave repeats in space. So if you have, for example, a snapshot graph where you plot a position versus y, then that distance between peaks is the wavelength. If you do a history graph, then that distance between peaks is now called the period. And the frequency is just 1 over the period. So, and then the amplitude is, in both cases, it's just the distance between the, I guess, whatever the x-axis is, and the disturbance, the maximum disturbance. And then the wave speed is the rate at which the wave propagates. And this is not at all related to the speed of the actual particles themselves. It's the speed of the pattern. And so in one period, it moves one wavelength, and that's where we get this equation. So I've shown you here now calculating V in terms of lambda. It's lambda over t, or you can put lambda times f. And all the units work out beautifully. Lambda is in meters, and period is in seconds, so this is meters per second. Or you could do lambda times f, where lambda again is meters, and frequency is per seconds. So you get the per second from the frequency. So either way that works out. So here's quick question number 1. Oops, I'll give you a minute for this one. Which is that here are 2 snapshots of 2 different waves, but they're moving in a medium in which the speed is the same in both media. Yep, question? No? Try again. So the amplitude, going once, going twice, you guys got it? The amplitude is bigger, I think, for this one. It's a little hard to see on this graph, but I think this A is a little bigger than this A. I don't know if less than one bamboo segment and bigger than one bamboo segment. Give me 30 seconds for this one. Which had the greater wavelength? Did it go? So I think it was this one. This is your distance right here, wavelength. So I got B. Which has the greater period? So both of these waves are traveling at the same speed. So which of these has the greater period? And this one, so I think the idea here is that the speed is equal to lambda over the period. So the period is equal to, not it's greater than, lambda over f. So if you have a greater lambda for this one, you also have a greater period. So I think it's B is what I was looking for there. And then last in this little sequence is which of these two waves has a greater frequency? 30 seconds. Yeah. So, and in this case, remember, the frequency is equal to 1 over the period. So if you have a greater period, it means the frequency is less. So this one has the greater frequency. All right. There's a fantastic energy in this room, and I'm really digging the vibe here. So let's go on to a couple different subjects here. We're cooking along through chapter 11, and the next few slides are about intensity. And this kind of gets back to amplitude. So we had this idea that even a small pulse and a larger pulse had the same wave speed. So what is different? Well, what's different about the larger pulse is that I get more of a high five. If I give a tiny little pulse, okay, I get a tiny little high five at the end. If I do a big pulse, boom, okay, I get a bigger. So I've transmitted more energy. So it's all about the energy. And in the case of a sound source or a light source, what you have is a source that's putting out energy in joules per second, I guess, because it's a continuous like, okay, so joules per second, that's watts. So the power of this source is measured in watts. And then the important thing about a wave is that it's not just the watts, it also matters what the area is. So it's watts per meter squared. And the reason for that is coming from this thing. So, okay, so what you're imagining here is you've got some speaker source of sound, for example, and it's in the middle of nowhere, like in deep space or something, or I don't know, in the air, I guess. And that sound is spreading out. So if the waves spread out uniformly in all the directions, down and up, and no energy is absorbed, so even if there's no actual friction or dissipation or scattering of these waves by the air, the intensity still decreases because it's spread out more. And this is where the area comes in. So all these little wiggly snake lines are all impingent on this smaller sphere that has some area. If you're out here at a larger area, it's again the same amount of power in watts, but it's now spread out. And if you have a particular size of ear with a certain hole in the side of your head or something, then if you're closer, you're going to take more of a fraction of all of that power into that hole in your ear. If you're further away, then with the same area, then you're taking in a smaller fraction of all that area. So what matters to how loud a sound is or how much you get from it is the intensity. And there's something called, I guess, a plane wave, where these are these spherical wave fronts, but you can imagine you're very, very far away from the source. So maybe the source is out here, maybe at infinity or something like that. And then these wave fronts are traveling along, and the intensity here is not actually changing with time. It's the intensity is power divided by A, where A is the cross-sectional area. So this is A. So sometimes I call it A, the area, or I call it the cross-sectional area, because the area that matters is the area that is perpendicular to the direction that the waves are traveling. So here the waves are traveling kind of down to the right. The cross-section area is these like windows. So the way you get more power through your window is you either crank up the power in the wave, or you could get a bigger window. And in each case, you'd have more sort of power going through. But the intensity is given by the power per your window size. And in a spherical wave, then what you do is you take the power of the source that you know is going in all directions, and you just divide it by all the possible ways it could go, and that's the sphere. And so it would be 4 pi r squared is the area of that sphere. That sort of makes sense? So that's why things are quieter when they're further away. It's because you've spread out the same power over a much larger sphere. And I think I have some examples. Let's go to the doc cam. So when I read on the back of this laser pointer, it says that it's a class 2 laser product, optical power 1 milliwatt. It actually says less than 1 milliwatt. So I've got 1 milliwatt of power going into this green beam, and it's creating a dot there. So what's really happening, it just looks like a dot, but there's an actual cylindrical beam of light which is going along. So we can try to calculate what is the intensity in that cylindrical beam. So let's do that. A laser pointer emits 1.0 milliwatts of light power. So the power is equal to 1.0 times 10 to the minus 3 watts into a 1.0 millimeter diameter laser beam. So what I think there is that the cross section is circular. Doesn't really say that, but I think we'll assume it. If it's talking about a diameter, I think that's got to be in a circle, right? So assume cross section of the beam, this is the beam, is a circle. And so the area of a circle is pi r squared. And we know that the diameter is equal to 1.0 times 10 to the minus 3 meters. So I guess the intensity, we're going to use I is equal to the power divided by the area. So this is not a spherical source spreading waves out into all directions. You see what I mean? All the light is in one little beam. And so it's not a spherically symmetric source. So instead of using 4 pi r squared on the bottom, you just use the area of that beam, which doesn't change as you go along. It's like a plane wave. So you just say 10 to the minus 3 watts divided by pi times 0.5. Don't forget to divide by 2. So r is equal to 0.5 times 10 to the minus 3 meters. And then you got to square it. And I get I is equal to 1273 watts per meter squared. And I can compare this if I guess I Google something like that. Intensity of sunlight. Which I got was 1364 watts per meter squared. So this sort of says to me that staring at a laser into a laser beam is just as bad as staring at the sun. A green laser. As bad. This is my evaluate step, as staring at the sun. Don't do it. Okay? Like if I took this laser and shone it right into my eye and was looking right at it, I could cause retinal damage. Okay? Because your retina at the back of your eyeball is covered with light-sensitive cells, which is great, but if you put too much light on there, it can damage the cells. And so also you shouldn't stare at the sun. Yes?
So why did he use 4 pi r squared?
I did not use 4 pi r squared because it's not like a light bulb. You turn it on, it shines light, fills up the whole room. But a laser, you turn it on, all the light is concentrated into a column that is not expanding.
So if it doesn't expand, you just use pi r squared?
Yeah, because it was a circular beam with the beam radius is r. Yeah, so it's the difference between 4 pi r squared, where r is the distance from the source, and as compared to pi r squared, where r is the radius of the beam. That's a good point. It's a bit. So what I wanted to do actually next is let's actually compare it to a light bulb. If you had a light bulb, how would that work? And let's say you had how far from a 100 watt light bulb should your eye be in order to have the same intensity as shining a green laser directly on your eye? So this is a case of a spherically symmetric source. So the bulb emits light in all directions. And so intensity is going to be the power divided by, I'm going to call it actually 4 pi d squared, where d is the distance now from the source. So the 4 pi distance squared is distance from the source. The r squared was just talking about the beam diameter. So, and I'm also going to assume 100% efficiency. So all 100 watts go into the light. And I'm going to neglect what goes into, I guess, heat, right? Heating up the bulb. This isn't a very good assumption, but it's physics. We can just make the assumption. I'm going to set I is equal to 1273 because that's given. And P is equal to 100 watts. That's given. And so we'll use I is equal to P over 4 pi d squared and solve for d. And so I just get that d squared is equal to power divided by 4 pi times I, intensity. And so d is equal to the square root of 100 watts divided by 4 pi times 1273 watts per meter squared. The meter squared is going to come up in the top. The watts are going to cancel. And I'm going to get the distance, is equal to 0.079 meters. So I think what this means is a light bulb held 8 centimeters away from your eye is as bright as a laser, or like the sun. So the sun's very far away, but it's a big star. And if you look at it, you can hurt your eyes. But you can make something as bright as the sun by holding a 100 watt light bulb 8 centimeters away from your eye and staring right at that. That's also kind of bad. So it's good to know that I think part of the moral of this story is that lasers are dangerous because you don't want to stick them in your eye and just shine it right in your eye. And it's something I can imagine my 5-year-old son doing, actually. I know this guy. He might do it. But most of us wouldn't do that, and it would hurt. And so you would want to not do it. You would go like this, and you would save your own eye. So they're really not that dangerous. Kitchen knives are dangerous as well, right? I mean, don't do it. Okay, are there questions on this one? Is this making sense? Let me see what's next on the list here. We're going through a lot of things, sort of rapid fire. Oh yeah, decibels. Yeah. You guys want to do some decibels? Well, I do. I'm in the mood for decibels. So first of all, let's look at some typical intensities. And there's this thing from the sun. Remember, sunlight at Earth's orbit was 1364 watts per meter squared. So that's one nice thing, is that if you had a 100% efficiency solar panel that was 1 meter by 1 meter and you put it on your roof, you get a maximum of 1364 watts out of that solar panel, I guess. Not that, I don't think that would power your dryer, but it would be something. And then there's things like sound. Sound intensities tend to be a lot less, so your ear is very, very sensitive. And in fact, you know, a whisper, someone whispering at 1 meter away is 10 to the minus 10 watts per meter squared, and you can hear it. So you can hear that. It turns out you can also tolerate being 4 meters away from the speaker at a White Stripes concert, and it's 1 watt per meter square entering your ear, but it actually sounds good because the music's so good. It's called the threshold of pain, as it turns out. So there's other things. If you're farther away from the sun and you use solar panels to power your satellite, you get less watts per meter squared, because that sunlight is spread out over a larger radius, I guess. A flash camera, one of those big cameras, can produce 4,000 watts per meter squared, but only for a very short amount of time. So not much energy, not many joules go into that. Again, also these fusion experiments, they can produce very, very short duration pulses that have extremely high intensities. So the amount of energy in these is actually a lot smaller than 10 to the 18 joules. I guess radio signals, again, pretty small, watts per meter squared. Inside your microwave oven, you've got electromagnetic waves that are going around, and the intensity of those waves, they're actually standing waves, goes up to around 6,000 watts, and so those can be absorbed by your food and heat up your food pretty quickly. And I guess earthquakes can have huge amounts of intensity as well. Okay, this is just reminding you what sound is. So sound is a pressure wave, and so you've got pressure plotted versus distance here, I guess, and the wave goes along. The molecules themselves are oscillating back and forth longitudinally, but what's the important thing is that you've got high density regions, pressure compressions here and here, and you've got low density regions, pressure rarefactions here and here. So you have ambient pressure, P0, the room pressure, and then you've got the pressure going up and down. So that's how sound works. And what's interesting about human hearing is that the human ear can respond to a broad range of sound intensities and frequencies. And I think I've asked Pius to bring a signal generator. We can look at frequency response on Wednesday. But the main thing to go over today is how the intensity is measured. So there's this terrible looking equation where you get the decibel system. So it's this equation, beta. So beta is a number that if you go to City Hall and you look at any sound ordinances or like laws, they will tell you about how many decibels, like if your party goes over 100 decibels as measured from the sidewalk, you can call the cops and then they can come. So that's like it's like a human-centered measure of sound intensity. Important to, humans. But this I right here is intensity, I guess, as measured by physicists. So the only thing that's really important to me, I guess, or to people that have to measure this thing, is physicists, something like that. Okay? And this is I. I is in watts per meter squared. And it's the real thing. It's how much energy per second per cross-section area is really getting delivered to your ears. But this beta is a number. It's measured in decibels, okay, which you can get from the intensity. And they compare everything to the threshold of hearing, I sub 0. So there's this whole thing. If you have 10 to the 12, then what happens is beta is equal to, for this one, 10 times the log base 10 of 10 to the 12 over 10 to the 12. Log base 10 of 10 to the minus 12 divided by 10 to the minus 12. So that's equal to 10 times the logarithm of 1, and this equals 0. Logarithm of 1, if you do it in your calculator, comes out as 0. If you do 10 to the 10, you end up with 20. And if you were to do 10 to the minus 11, you get 10 decibels. Oops. If you do 30 decibels, that's 10 to the minus 9. So the pattern here is that the decibels go up by an additive step of 10 decibels every time the intensity goes up by a multiplicative step of times a factor of 10. All the way up to, like, the threshold of pain is 120 decibels. That's gone 1, 2, 3, 4, 12 steps up. So that's 10 to the 12 times more intensity. For each step is 10 decibels. Does that sort of make sense? Want to do a want to do a learning catalytics? No? So, going back to our definitions, 10 decibels means that you're 10 times more intensity than 0 decibels. That's sort of definition. So this sentence, a sound level of 20 decibels has blank times more intensity than a sound of 0 decibels. Give you a minute. Survey says, going once, going twice. Stop. Okay, well done. So most people were getting it's 100 times more. And actually one of the ways that you could do this, I guess, is I could say, remember that beta is equal to 10 times log base 10 of I divided by I0. Okay, where I0 is that the 0 decibel thing. You can solve for I, just for fun. The way you do that is first I'm going to divide both sides by 10. So beta over 10 is equal to log base 10 of I over I sub 0. And then I'm going to use the fact that, this is a math fact, that the 10 to the power of log 10 of x equals x. So I'm going to raise both sides 10 to the power. So 10 to the power of beta over 10 is equal to 10 to the power of log 10 of I over I0. And that's just equal to I over I0. So then I is equal to I0 times 10 to the power of your beta value divided by 10. So in this case, you've been told beta is equal to 20. So when beta equals 20, then I is equal to I0 times 10 to the power of 20 divided by 10. Or 10 to the 2 times I0. So it's 100 times more. That's how you use logarithms. Sorry for getting so mathy, but you can blame city ordinances. I didn't invent decibels. It's not the physicist's fault. It's something to do with this idea that the ear is responding logarithmically. The human ear is able to pick up very, very low intensities while simultaneously not being too annoyed by very, very high intensities. Let's do this one. Let's say you have your sound playing at 50 decibels, but then you crank up the volume to 80 decibels. How much have you increased the intensity? Give you a minute to think about that. Okay, you guys got it. So this is, again, 3, I guess, steps of plus 10. So it's 3 times of 10. So 10 times 10 times 10 is another way of saying it. That's 1,000 times more intensity. Okay. So next thing I want to talk about is principle of superposition. And someone was pointing out during the break that if I send these waves, like 4 of these waves come back. And so at some point during this time when there were still these, one wave had hit and there was 3 going this way, there was 1 already traveling to the left. So we have this weird idea that with waves, so there's the motorcycle goes along, it hits the brick wall and stops. And that's kind of what we're used to. With waves, they don't do that. They can pass right through one another without affecting each other. You can send a negative pulse and a positive pulse, and they somehow just remember what they're doing and just keep on going. So I think what we're showing here is there's a dashed blue line which is traveling actually from left to right, and a dashed red line which is traveling from right to left. When they meet in the middle, they combine. And so the black line is what really happens. So at the point where they're together, they just add up somehow. And so this pulse, this gets twice as big when they get together. So this is called the superposition principle. Mathematically, it is extremely simple. The disturbance of one is called y1. The disturbance of another one is called y2. And if the two waves overlap at the same position x and at the same time t, then you just take those two waves and sum them up, and that superposition is the disturbance. But what's neat about this, and this is where you got DJ Buzzcut, is that the disturbance can be below or above your ambient pressure. So this is where you get noise-canceling headphones. If you've got some loud noise which is coming along, and you play that exact same noise at the exact same amplitude and frequency, but you flip it, so it's anti-noise, and you play it into your ear, the two things will cancel out and you'll get silence. So this is what's called, there's constructive and destructive interference. So this is wave interference. You have two waves. Principle of superposition is they just add. If they add to produce a larger wave, larger amplitude, that's called constructive interference. If they add, but one's negative and one's positive, and you get a smaller amplitude, that's called destructive interference. So what you'll see DJ Buzzcut do is he'll turn on one sound, turn on the right speaker, boop, turn on the left speaker, boop, turn them both on together, get nothing. Okay? Somehow they cancel each other out. This is an important skill. Can you add the triangle plus the rectangle wave? They're both going 1 meter per second. Triangle is going to the right. Square is going to the left. I'll give you a minute to add those up. Yeah, a triangle plus a rectangle equals a house, I guess. Something like that. So I think, so this is this rectangle now. If I do it 1, 2, 3 seconds later, it'll move 3 meters to the left, and it'll look like that. And if I look at just the triangle, for example, let's choose green. This is the triangle now. So 1, 2, 3 seconds later, it'll be like this. So we add these two up to get the blue line. I'm going to get something like, it'll actually start up here. And then as this goes bigger, it'll just add them up and then down to be here and then down to the bottom. So it's exactly this. Okay, so that's a neat thing. That's interference. There's 3 things that happen from principle of superposition. There's interference, standing waves, and beats. I don't have time to talk about beats today, but I'll talk about it on Wednesday. But standing waves are kind of neat. So what you may have noticed is that when I had the rubber hose, I was sending pulses, and that was fun. But what I didn't do is kind of the obvious thing, is to send a sine wave. And I'll tell you why I didn't send the sine wave. Because when you send a sine wave, it does that. It's the weirdest thing. You'd think you'd get something really cool, but instead you just get this. So that's what's called 2 sine waves that are going in opposite directions, and it's called a standing wave. It is truly the boringest thing I could do. But it's rather profound. This is exactly what happens, for example, when you pluck a guitar string. It just goes up and down like this. It's called a standing wave. And I guess you can do fancy things, like you can try to increase the frequency by doing a faster thing. Oh. And then you get, this is a different kind of standing wave in which there's a node in the middle. The first one is the fundamental mode. I think I can try for a 3. Whoop. Again, just have to increase the frequency. 1, 2. So there I've actually got 3 intermediate modes. This is, looks like 4 antinodes there. Just kind of weird. But this is what you always get. I'm sending a sine wave from left to right. There's a reflected sine wave going from right to left, and somehow they combine to form this really weird, boring thing. I can try to do it with this, but it's hard to do. It's not what you would expect, is it? It's weird. There's even spots where it doesn't seem to be moving at all if I get it just right. They're called the nodes. Again, this isn't really working. It's hard to set up a standing wave in this thing, but you can try it yourself after. Okay. Standing wave. Okay, so the math is really brutal. but let me just walk you through it really quickly. Yeah, so I don't know if you remember me telling you that if it's cosine of something with the minus, t minus x, that represents a sinusoidal wave traveling from left to right. If you have a plus sign in it, then that means you're representing a sinusoidal wave that's traveling from right to left. So this is the original wave, and you add it to its echo. Then you do a trig identity. There's something like cosine of alpha plus beta plus cosine of alpha minus beta. It ends up being sine times sine. So this is really weird. All of a sudden, what you've got is simple harmonic motion. This, let's go to red. This part right here is simple harmonic motion. Okay. It's just, well, it's sine instead of cosine, but it's 2 pi over t times t. That's what we saw before. And this is some sort of position-dependent amplitude. So every particle just goes up and down, but the amplitude that it goes up and down depends on position in the sine wave. Amplitude. This is almost like an envelope. I don't know if you remember the envelope function that we did when we had damped simple harmonic motion, where as the time went on, the amplitude went down. Well, here we have an amplitude, an envelope function that varies with space and is actually periodic. So you have points where the sign is 0 and the amplitude goes to 0. It's called a node. And you have points where the amplitude is maximum. And so what you see in a lot of textbooks is this drawing right here. This is actually 1, 2, 3, 4, 5 different snapshots of what's really happening, which is this. This is like a perfect standing wave. It goes down, it goes up, then there's a node where nothing happens. It just sits perfectly still. You can put your finger on there and it's just, nothing's happening. You can hold your finger right there. No motion. Then another antinode, but it's moving opposite to that one. Then another node, antinode, node. And what's cool about this, everybody's beeping, including me, is that the wavelength is twice the distance between adjacent nodes. So let me write that down. Can you see why? 2 times distance between adjacent nodes. This is a factor of 2 that everybody gets wrong. And it's a good question for like a test or something. Because what this represents is that it's going up and down like this at one time, and then later it's going like this, straight, where everything's just flat, and then later it's going like this. But the wavelength is actually this distance from here to here. Do you get me? Anyway, that's the thing about, and I can put it on learning analytics as well. Might be the last thing I do here. What is the wavelength of this standing wave? I'll see if I can do this actually. I'll put you a minute. That's your minute. Right. So yeah, I think it's 1 meter. Because this is the actual wave. It's going like that. So when it repeats, it's actually 1 meter is the wavelength there. Okay. That's actually all I've got for today. So I'll see you Wednesday.